This animation explores the destructive power of nuclear weapons. Nuclear warheads can reach their target via intercontinental ballistic missiles launched from a silo. The Minuteman III is a multi-stage missile that separates its first stage after about 1 minute. Shortly thereafter, the shroud is jettisoned. The rocket continues to gain altitude and speed with the help of the second stage. After about 2 minutes of flight, the second stage is separated. The third stage finally increases the speed of the missile to over 16,000 miles per hour. The warhead and fourth stage are now in free flight. The fourth stage can increase the range if required and is used, among other things, to precisely aim at the target. After the warhead has been decoupled, it is rotated for trajectory stabilization. The friction of atmospheric particles causes the warhead to generate a lot of heat when it enters the atmosphere. The warhead hits its target with a speed of more than 2 miles per second and explodes. The result is a flash of light brighter than the sun and temperatures in excess of 100 million degrees Celsius. Completely new materials and structures, such as trinitite formed from sand, are created by the high temperature of the explosion. Now let us take a quick look at how an explosion of this kind is produced. In order to do this, you need to have elements that can sustain a chain reaction, such as plutonium-239. When a neutron hits the plutonium atom, the atom splits into different fission products and emits 2 or 3 neutrons, which can fission other plutonium atoms. This fission causes neutrons to be emitted again. A chain reaction begins. For a chain reaction to occur, certain conditions must be met. If the material has too few plutonium-239 atoms, only a few neutrons are produced, and the chain reaction will proceed too slowly. In addition, certain atoms absorb the required neutrons. In nuclear reactors, the proportion of plutonium-239 atoms can be increased by nuclear transmutation. In this configuration, the chain reaction is already faster and more efficient. However, neutrons can leave the material and thus prevent further chain reactions. For this reason, the material is formed into a sphere, and a material that reflects the neutrons is attached to the outside of the sphere. In this way, these neutrons can trigger more chain reactions. In the next step, the plutonium must be compressed so that the atoms are closer together. Only then can the chain reaction take place efficiently enough. Enough neutrons must be released at the right time to make a nuclear weapon. This is the chain reaction of a nuclear bomb. A very simple nuclear bomb therefore consists of a neutron generator, a plutonium sphere, and a tamper that serves as a neutron reflector. It also requires explosive lenses and the necessary wires through which the explosives are detonated. When the explosive lenses are detonated, the plutonium is compressed, and the neutron generator releases neutrons. The chain reaction then begins. The simultaneous splitting of the atomic nuclei leads to a fireball with a temperature of over 100 million degrees Celsius. The resulting pressure and temperature even enable nuclear fusion, in which two atomic nuclei fuse and release a neutron. For this reason, modern nuclear weapons not only have a fission stage, in which atomic nuclei split, but also a fusion stage, in which atomic nuclei fuse. The fission stage has a hollow plutonium core. Conventional explosives are used to compress the plutonium. In addition, a container is attached which produces a gaseous deuterium-tritium mixture in the hollow plutonium core before the explosion. This mixture serves as a neutron generator. The fusion stage has a uranium-238 shell. There is also a layer of lithium and deuterium. A uranium-235 core, which can also be filled with lithium and deuterium, is also part of the fusion stage. As soon as the first stage is ignited, the plutonium emits gamma and X-ray radiation as a result of the chain reaction. This radiation and the polystyrene foam, which becomes a plasma, generate high pressure on the second stage. The second stage ignites. The neutrons produced by the fission of uranium-235 atoms generate the required tritium from the lithium. Due to the high pressure and high temperatures, tritium and deuterium atoms are pressed together so that they fuse and form neutrons. The fusion of atomic nuclei is known as nuclear fusion. Nuclear fusion releases even more energy than nuclear fission. This means that smaller bombs with even more explosive power can be built. Let's take a closer look at the individual phases. A nuclear warhead with an explosive force of 300 kilotons pulverizes all matter within 1,500 to 2,500 feet. At 300,000 degrees Celsius, the chemical bonds of molecules that hold the atoms together are broken. An almost unbelievable heat sets fire to everything within a radius of about 3 miles. The heat, which has spread at the speed of light, is followed by a pressure wave that sweeps away everything in its path. Here again we see the spread of heat radiation and then the shock wave. A few seconds later, the blast wave is followed by a blast wind of negative gauge pressure, which sucks everything back in towards the center. The destructive power of a nuclear warhead with 300 kilotons of explosive force can be seen here once again. The actual impact will depend on a number of factors, such as the weather conditions. Fires spread quickly, partly due to open gas pipes that were destroyed by the blast wave. For this reason, not only the explosion but also the fires release toxic substances into the atmosphere. With over 4,000 operational nuclear warheads, it can be assumed that not just one, but many nuclear explosions will occur. Everywhere in the world, in larger cities, and where the enemy's nuclear weapons are stored. In the case of a ground burst, the radioactive substances released during the explosions combine with larger particles of the environment. This releases a large amount of radioactive material into the atmosphere. Dense, black radioactive clouds slowly but steadily envelop the entire globe with the help of the wind. Even the most beautiful, sunny, and remote places on Earth are about to experience a nuclear winter. The black clouds push in front of the sun and lead to months, possibly even years, of darkness. The radioactive particles fall down as so-called radioactive fallout and can harm humans, animals, and plants. Soon, black rain will turn every plant on Earth black and contaminate the soil for decades, possibly even centuries. Crops will die. Food will become scarce. And once flourishing landscapes become barren wasteland, our blue planet is starting to look like Mars. At the end, let's look at just some of the numerous effects on the human organism. Our eyes have the ability to control the amount of light reaching the retina. If too much light falls on the retina, the iris constricts the pupil. This allows only as much light to reach the retina as it can process. A nuclear explosion produces a flash of light that shines brighter than the sun. This can damage the retina and cause temporary or permanent blindness. If you are not in an enclosed space, the intense heat generated can cause severe burns even far away. Radioactivity can also occur at a great distance due to radioactive fallout. Radioactivity is dangerous because certain substances emit small, fast particles. These particles can knock electrons off other atoms. Our DNA is also made up of atoms. Indirectly or directly, this ionizing radiation can cause breaks in our DNA. If the cell cannot repair these double-strand breaks, it initiates apoptosis and dies. If this happens too often, the entire organism is at risk of death. If the cell does not die, it can become a cancer cell. It then no longer performs the tasks characteristic of its type. We say it degenerates.